Okay, so thanks for having me. I'm so happy to be here. I spent a while thinking about what to talk about for this chat. So, um, I decided to talk a little bit about some of the slightly older work that we did on predictions. We're really looking at some of the limitations and I think some of the challenges with some of the data and just some of the things that we struggled with a little bit, and then talk a little bit more about some of the collaboration or collaborative work and how we're looking at how we could take some of these prediction models and put them into robot planning in interactive settings. And I think um, I might tease a little bit and poke and prod because I was hoping we could at least have a little bit of some discussion and whatnot here, since this is the community to have it with. So first off, all the work that I'm doing is by now doctors Zhe Huang and Shuijing Liu, among others in my group. So you can thank them for all this stuff. All right. First off, this is such an amazing area, and there's so much work in this area. I'm glad I'm the first speaker, so I can pull up this plot and pay homage to our program committee. But this is a wildly popular and growing area. And so even though the survey by Andre here is ends in 2019, this is just a GitHub. Supported by Yishu, who collects and curates all these papers. So it's an ongoing effort that I enjoy. And even though this isn't a great proxy, this is, the number of stars he's getting. So, it's also growing. So even though it's not quite number of publishing, there's a lot of interest and a lot of hype in this area. So when we start thinking about what we can actually do in terms of research contributions, I kind of start thinking, like, now what? Lots of people are publishing. There's always new algorithms. There's always new stuff. So what do we do to really make a difference? So I started sort of thinking about what are the two big things. The now what, you have some model. So I think there's one thing where we can start diving a little bit deeper. So we can start digging it a little bit more and maybe rethinking some of the assumptions that we've been making, rethinking how we do things, maybe dive a little bit more. And just to throw out some, examples, one of the things that we've been doing in my group is rethinking about whether or not we're actually calibrating all the uncertainty that we have when we have these stochastic models. So when we, say something, we say it's Gaussian. Is it really Gaussian? Doesn't matter if it's Gaussian. Just kind of thinking about some of these things that we kind of take for granted when we are applying and using some of these algorithms. The other thing that we can do is, again, put them to use. I'll pick on my own paper, but I think almost every paper in prediction has something at the end that says something like, in the future, we will put it into a planner. And whether or not that happens is sort of up in the air. So you can put these into things like throw it into an MPC. Sometimes it works, sometimes it doesn't. I think it seems like it's sort of a trivial problem, and I think that's something we kind of take for granted. And we put a lot of effort into the prediction part, so we should make sure that it actually works in the planners. One of the things that we found when we were integrating this stuff into some MPC-like planners is actually very hard to get things that are context or decision dependent. So as you are actually implementing in this in the planning and the control loop, you start getting some changes in the model. So you really have to not just have traditional predictions, but things that are dependent on the actions of your robot. So this kind of nesting behavior is something that's generally challenging. So that was just sort of some teaser things, some quick things. But so today I thought we'd talk about sort of two pieces in this. So first we'll do one kind of in this dive deeper thread, looking at some of the, I think, the assumptions that are made in the data sets that we use and thinking about ways we can approach them. It's not, the only solution, but it's one thing that we've looked at, and looking at how we can create interaction graphs. And then the second, in how do we put them to use? So we'll look at some work that we've been doing in crowd navigation and how we were able to integrate our prediction algorithms into reinforcement learning contexts. And then at the end, I'll just throw out some more food for thought. So, for example, do we actually need these fancy trajectory predictions, and maybe some things on food for thought for when we actually think about robots and humans interacting over longer terms. All right, so with that, I will jump right into this first bet. So diving a little bit deeper. So when we think about a lot of the data sets that we use in these multi-agent trajectory predictions, we often set the problem up in this way. So we have, hopefully you all can see my mouse here. But we have some observation period. This is hopefully something that everyone's familiar with. And then you have some algorithm that takes in this observation and spits some prediction time horizon out. This is a long-term prediction, so we hope this is long-term. And there's two assumptions that we usually make when we do this. So first off is we often have some assumption or some hack to make it seem like all agents are all observed. So for example, if we look at, this is a plot from one of the which data set is this? One of the common benchmarks here. So we have our observed trajectories here in blue. So you can see we have these observations that we have. We have the observed trajectories. If they are in red, we have these like fully detected. So we have the agent that is there for the full observation window. So this is like the kind of ideal point. But if you look at even just this scene, all of these orange forward prediction lines, these are agents that only have partial predictions. And in general, these are often thrown out. Maybe we do some padding. We kind of hack around how we typically deal with this. The other point here is that all agents are influential. So we all often have something where we have a sort of a stack of all the information that's coming in, of all the agents that we detect, and we put all of it in, which may or may not actually be useful, but we kind of just take all the data that we have and all these observations here. And I should have had these popped up earlier. So all these agents are the ones that are not fully observed. So they're only observed for part of the observation window. Maybe they pop into the scene. If you're thinking about a robot deployment, maybe they weren't in your tracking algorithm. Maybe you had some occlusions. But basically, it's almost as if these agents don't exist. So it's something like 41% of pedestrians actually get cut out if you look at this in the benchmarks. So what does this mean? This probably means that we either have to pay special attention to it if we really want to think about how we're going to put this on a robot where this is a real problem. And again, it kind of affects how what is actually happening if we think about the different agents interacting. So even if we don't include an agent because they're only partially observed, they're still influencing the other humans around them who may actually be observing them. So we came up with some approaches to start thinking about how we can encode all of this information over time and try to both make our approach flexible enough so we have a principled and structured way to incorporate partial observations, and also try to really capture all the interactions between different agents. So let's look at a little bit of a toy example here. So all of these different shapes are different people in some scene, and say we just have some observation window, say this 4. So this is kind of the ideal case where we have a full observation for these two agents. And here we have some where we only have a few instances. So they come in late. Maybe we have some drop sensor measurements. Many things could be causing this. So what we started thinking about doing was trying to basically come up with a graph structure that can help encode how these agents are interacting. So we have a graph that can represent all agents in a scene. We highlight the ones that do exist. We do have some, self interaction. And we can draw some, basically some lines between the agents that are present. And we can do this at a certain time step. So in this time step, the farthest back, we only have 2 agents that we have detected. As we move forward in time, we get another agent that comes in. We can create a graph that represents all of these agents that might be influencing each other. And as we go up to that point in time where we have all of these detected agents, we can have this fully connected graph here. So this is kind of a nice structured way we can think about at every time step, how we can encode who is there and who isn't, and it can evolve over time. As I hinted at, this isn't that different from what most people do. Graphs are nice representations. I can go on about that some other time, but this is kind of a nice way to capture that. But one thing we can start thinking about is if we actually need all of this information at each of these time steps. It could be that some of these agents are far apart. They're not important. We don't need to think about the interconnections and the influences between all of these different agents. So we started thinking about how we can come up with a sparse interaction graph. So say we pick one of these time steps, we can come up with some one of these graph representations. We can start thinking about how we can prune this down. So for this, we pick some target. In this case, we have, let's say, a pedestrian circle here. And we start thinking about all the different edges between these different agents, including themselves. And we start thinking about if we can come up with some method for identifying if this is important or not. So we basically do this by looking at this Gumbel softmax here, some self-attention where we can start basically thinking about which connections in this graph, which features here are most important. So this helps us basically come up with a tighter representation that basically helps identify which agents are actually influencing each other. And I'm kind of being wavy about training here, but we do it sort of end to end. So it's going to identify the agents that are most important when we're actually evaluating the end prediction for the full trajectory. But we do this for all of the different agents in our scene. So we come up with a number of different connections between all of them. And note that we don't have to have, we pick some n for some sparsity constraint, but it doesn't have to be that. We can only have one connection if that makes sense. And then we compose all of these graphs together and we get what we call a sparse interaction graph. So it's basically a compact representation or something that's a little bit tighter from all this. So if we think about passing this through, we have our fully connected interaction graph, again, based on who is ever present in the different scenes. We have our selector that basically identifies which nodes and which edges are important. And we get some reduced graphs. Again, we have this sort of tight representation that allows us to be dynamic with how many agents are in, and we don't have to worry about doing any hacks like padding or anything like that when we have these partial observations. From that, we have some temporal encoding and whatnot here. Nothing too fancy here. This is what is commonly done in graph neural networks here, but it basically helps us come up with a nice feature representation for that interaction graph at that particular time, which we can then pass into a whatever model you want. We used a simple MLP. We trained this, and this is how we basically trained our forward prediction model. So to just loop it all together, since I've been talking fast and kind of hitting things relatively fast here, we have our interaction graph structure. So we're basically encoding the scene in a compact way that is amenable to partial observations. We are reduce this down, so we're having this graph represent the important connections between different agents based on the context and the scene and everything that goes into our algorithm. We have some encodings. We use transformers for this. So we have both spatial encodings and also temporal encodings. The temporal encoding is actually fairly important since there is some history. So if we think about what is important and what you're sort of attending to, what is interactive at a later time step, you might have some information from a previous time set. So I'll touch on that later. But then from here, we pass this into our predictor and we go forward. So this is kind of the full loop here. So basically the main insight here is a lot of this is fairly typical from what you would do for any prediction method, but we've really imposed this graph structure that kind of helps us be resilient to, again, some of these common issues. So we looked at many of the benchmarks. This paper is a few years old now, so it's there's probably shinier methods we could compare to, but there's a few different things that we can do. I guess first off, I don't expect you to read this full paper, but we did all the metrics, we're comparable. The important thing I think to note from here is we can actually visualize the graph at different time steps, so you can actually see which agents are important for predictions at different times. So it's kind of a nice way to sort of see what agents are actually important. It's a little bit blurry because we do have this time encoding. So just because it's not immediately present doesn't mean that they weren't influenced. So at some point in your observation, but we kind of have this nice representation here. So let's look at a few qualitative results to just get some idea of what's actually going on here. So we can visualize this attention. So this is an adjacency graph. So this is highlighting the sort of the attention or the weight that goes between different agents. So in this case, we have up to 7 different agents. We have our robot included here. Here's this robot, and we have a bunch of pedestrians coming around. So if we have a fully connected scene, We're not fully connected if we have a low sparsity constraint. So we're saying we're almost fully connected. We're only dropping a few unimportant agents. We're almost attending to all the different agents at different times. If you drop this parameter down, so you enforce really intense sparsity constraints, you're basically just attending to one or two different agents at different times. Some things are a little bit perhaps not intuitive. Like you might think that this immediate agent is always important, but there is that temporal component, and we have a good idea of what's going on there. So with more sparsity, you can see that the motion of the agent isn't as impacted by not important neighbors. So you tend to have a smoother path where you're only impacted by, again, what we think is important here. So we can see this again. So this is if you have full connectivity. If you're in really dense crowds, you can actually get overwhelmed, which is one of the main inspirations for this work. Whereas if you are trying to be selective with what you're attending to and what you're reactive to, you can handle complex crowds and whatnot here. And if you have partial observations, you can be much more resilient. So in this top case, we're actually controlling these agents, so it would have gone into a collision. So it has sort of a emergency stop that comes in, so that wouldn't have responded. Whereas we have a nice response. We are able to adapt to this partial observation in a very nice fluid way. So again, we've been looking at this. We did some studies looking at how sparse you need to be. The tricky thing with this method is it does depend on the density in the data and sort of the scene. So it's not something like I can say like, okay, yeah, you always pay attention to three pedestrians. You kind of have to tune that parameter. So for each different scene in the major data sets, we had to pick a different end. So that's one of the sort of dirty laundry bits, but it still works reasonably well. It's relatively fast, and it's something I can augment most sort of core methods here. Okay, so again, the main thing that I wanted to hit home here is, again, we just started thinking about what are some of these assumptions, and I think we came up with some kind of interesting insights from there. So I think there's interesting work that everyone can do if we start really challenging some of these assumptions. So that was sort of the dive deeper tidbit. So now let's think about how we can put them to use. So we're going to use the same algorithm that we were just talking about, a sparse interaction graph. We're going to look at how we can encode this into or incorporate this into reinforcement learning crowd navigation. So I don't think I really have to explain what crowd navigation is, but the basic idea is you have a bunch of humans around you. You want your robot to get to its goal. The hope is that if you have some forethought, you have this pedestrians, you can be more proactive. Hopefully you can be safer, all this stuff. So there's been lots of work in crowd navigation. It's a very popular area. If you look at dense crowds, when there's lots of people around, traditional model-based approaches tend to fail. RL approaches also tend to fail. They tend to inherit a lot of the problems from model-based approaches here. And just in case this little graph isn't clear, we have our little yellow robot here. These are human agents. We're trying to get to our point. But typically in dense crowds, we tend to have these situations where you tend to have like the freezing robot problem. You just kind of get overwhelmed by all of the different agents around, and you kind of get stuck not knowing what to do. And we were really interested in even much more dense crowds in that scene. So we really wanted to see how we can look at these very realistic, heavily crowded scenarios and really think about how we can get the robot to navigate in these settings. And again, if you look at model-based approaches, they tend to fail. If you look at common RL approaches that can handle the previous dense crowds, when you get to really dense crowds, they tend to still fail. So what we wanted to start doing is, again, building on this idea of trying to focus our attention on different agents, trying to select which agents are important for us, try to build off of our prediction models and see if we can have similar outputs, so we can have better goal reaching and better navigation. So following the similar theme, you can maybe guess what my group these days likes to do. We can come up with a graph representation to help the RL algorithms at all. So just to give a little bit of a background on how our baseline crowd nav stuff works. So we have all our detected humans and robots. In this case, we only have one robot here. But we basically cast this as a spatiotemporal graph where we have this factorization where we're basically looking at the edges and connections between all the different humans and how they impact the robot here. And if you just have basically this connections and you just use this in your RL algorithm as your architecture, this is where you can get something that can work pretty well in somewhat dense crowds. But if you get to our scenario where we have really dense crowds, it still tends to fail. So there's still not enough foresight in the RL algorithm on its own. So as you can probably guess, we started thinking about how we can take some of these prediction models and toss it in. So building on the same structure, we basically come up with a add to this graph, and we pass our predictor output into this. So we do the same kind of encoding, similar to how we do all these other encodings in a graph when we add this prediction. In our case, we are not actually training this with the RL algorithm. So this is a frozen predictor. So we have basically you can plug and play with your off-the-shelf prediction, and you can pass this into your RL algorithm here. Okay, so we can think a little bit about some of the reasoning and the structure. So the graph structure itself, this works pretty well, even if you have no predictions. So this kind of reasoning between different agents, this graph structure, it's all good. That's not why we're here. So let's get to the predictions part. Oh, and I can look at some of these baselines here. So in this last bit here, this is where we look at the impact of predictions. So if we just have straight predictions, like if you were to just say, I'm going to treat this all as some a stack of trajectories and just put it in and do no extra work. So don't think about how to encode it in this graph-like structure or anything. It tends to get overwhelmed. There's just too much information. Maybe if you had a ton of time and a ton of compute, you could do it. But for most reasonable people, it just doesn't work. So you can't just toss your prediction in that well. So if you start thinking about adding this structure, though, that's when it gets a lot better. Okay, so again, the impact of predictions is that you tend to have this more foresight. You get all these kind of nice things that you might expect. Things are more socially aware. Things are safer. You know, everything that we preach in this workshop. One thing I did want to note is one comparison that we did. So we have this GST. That's the model we presented in the first half. So we have this, and this gives us our best performance. We have high success rate. We do really well in social metrics. This is good. It's capturing human behavior. You know, it's doing all the things. It's checking all the boxes. That being said, if you put in just a simple constant velocity model, you also do pretty well. So just giving and kind of encouraging any foresight is good. So this is sort of hinting at that bit that I kind of probed before, that maybe we don't need the fanciest model, but any prediction is pretty good. So there's that. And here's just another video. We've kind of been seeing these before. Agents move around and they work. And more importantly for us, let's see if this video will play. We were able to put it on a robot. It was able to work outside. This is, I think I only have the video for outside here, but we have it on inside. We have it in a bunch of different places. So we have it on Illinois' campus. This is at UT Austin's campus. So it works reasonably well in a number of different places. So, okay. So I'll start wrapping things up here and just drop a few notes on food for thought that I think might be worth chatting about. So the first point, do we need fancy trajectory predictions? I kind of hinted at this. For interaction, sometimes we don't. So actually, I spoke at this workshop, I think 4 or 5 years ago. And I talked about some of this work where we were working on incorporating intent into our predictions. So if you have a estimate of what the human's goal is, you can do a better job doing predictions. This is quite intuitive. The snippet that I put in the beginning about how we'll put it in a robot system was actually from the end of this paper. So we did try to do that. So we were looking at how we can have collaborative robots working working with people on a joint assembly task. It basically built up and kind of expanded this the structure quite a bit, where we are now, instead of tracking pedestrians through space, we said, hey, we can predict hands as well. So we were looking at how people moved as they were doing some assembly tasks. So we did the same thing. We had some intent structure that we built up. We built up our full model of prediction, and we were able to get some kind of nice stuff working. But that being said, we kind of found something similar to what I hinted at with the crowd navigation. It turns out that for a lot of this stuff, maybe it's because it's a small area, for the task, the fancy prediction was totally overkill. We ended up just using a really simple constant velocity model, since everything was so fast. We were really looking at how the robot can interact with a human on a pretty short time scale. So the quick update and quick feedback was enough, and we didn't actually need the fancy prediction. But the estimating the intent and having this higher level structure of the model of the human was really important. So thinking about different levels of abstraction for prediction can be very useful, regardless of task. So thinking about the situation and the task, I think, is important down the road. The other little bit of food for thought before I get kicked off the stage here. So in this workshop, we're often thinking about long-term predictions. So we're thinking about things, seconds, minutes. I don't know how long we're trying to push for now, but one thing that we can also think about is long-term or iterative interactions. So we've done some work where we've been thinking about how human behavior changes as it interacts with people more. So this is just a simple case where basically we have a simulated crossing here. So we have a little drone here. It's going back and forth across this room. And the human is also crossing here. So we have initially the human is very hesitant, almost always yields to the robot. But as they start having more interactions, they kind of realize that they can kind of bully the robot. So they start basically just passing, and they kind of ignore the robot. So when we were thinking about this, part of what we were kind of got us here is we were thinking about how these human models and the predictive models change over time, and how we need to be adaptive and responsive to these different pieces. So that's just something I think we can think about a little bit. So, okay, I'll just quickly wrap up. So, again, today I just probed a few questions, some food for thought about how we can address some data set challenges, how we can incorporate them into predictions, at least one way that we found worked for us. Again, we like this graph structure. We think it works quite nicely for helping us sort of identify what is actually important, what's actually meaningful in predictions. So with that, I'd like to thank my students. Again, most of this work was by Zhou Huang and Shuijing Liu, who are now graduated and off doing great things, and NSF for sponsoring this work. So with that, I'll take questions if I have time. I'll leave some of these videos going. We have a failure case here that, so I'm being relatively honest. I like this video because I think it's important to note that humans aren't always the problem. Sometimes it's other things too. It's also a video down here. We were doing just some experience, and we found that actually a lot of times when people came in unexpectedly, they just kind of ignored the robots. Also, maybe we don't need to predict them. Maybe they'll just avoid us altogether. So anyways, with that, if I have a few minutes, I'll take questions.
Let's give a round of applause for Katie there. So yeah, Katie is a very enthusiastic speaker. So we can only have time for one question or two. So yes, I see you raise your hand first. So go ahead, please go to the middle of the ion. Yeah.
Hi, thanks for the great talk.
Thank you.
There was one part I was wondering. You said that the constant velocity model approach was also doing quite fine. So my question is, do we really need fancy algorithms to predict a little bit better, or can we just take the constant velocity model?
I think so. I think the most important thing is every application, every setting is pretty different. So I think in our case, also because we were so reinforcement learning kind of also hacks around the problem because it's building up its own model a little bit too as it's making its decision. So it learns a little bit about how the model or how the world evolves. So providing the prediction just kind of helps it a little bit. So I think maybe with reinforcement learning, you don't need as much of a fancy model because it's already learning sort of how everything is evolving over time. So maybe not as much for that. It probably is more useful when you have more, I hate the term traditional models, but if you have something like MPC or whatnot, where you're not actually learning the world model, then things like that could be more important. But I think it really comes down to the task in time horizon, because I think it's if you're operating on short time scales, the difference between your fancy model and the constant velocity are probably not that different. Yeah.
Thanks.
Yeah.
Okay, so maybe we can take one more question, and if the next speaker can come up and start setting up, that would be great. Yeah, go ahead.
Yeah, thank you for your presentation. So, so we come across a similar problem that for the pedestrian interaction, so we can predict the pedestrian behavior, but for the environment that include both robots and the pedestrians, and we know how the robot, we can design some algorithms to allow the robots navigate in the pedestrian-rich environment, but we don't know how the pedestrian interact with the robot, and we don't have the data set. So how to address this problem?
Yeah, this is a great question. Actually, when with our, I didn't put them in here, but when we were doing our crowd nav work, so we had the deployments that are kind of like real world, they're kind of navigating around. But to be honest, I think the more informative experiments we did, they were kind of like staged, where we just had like 4 people. We told them where to walk. We told them what to do. We told them to like either ignore the robot. We told them to give them birth. We told them to bully the robot. And we kind of probed the setup a little bit more. So if you have this is actually something where if you have a good model of these different agents and you're able to detect them well, then it actually works pretty well. So one of the things that we did was, but it only worked in some small settings, so I don't think it actually made it to the final bit. But if you can try and come up with a trait model of the different people and estimate like, okay, is this person going to just avoid me? Maybe I can ignore them. And again, thinking about this sort of like higher level traits and behaviors, that was actually pretty useful for those like specific contexts. Yeah. But I'm happy to talk more about this because I think it's a fun problem.
No problem. Thank you.
Okay, let's thank Katie one more time. Thank you.